Hello, this is Mr. Roosh, and this is the third in a series of talks on a first-year calculus class. Thanks for joining us. Yesterday, we talked about an operation on a function. The first day we talked about functions, and we said there would be four things we do with functions. One, something you've done for a couple years, just plugging something into a function, getting a result. That can be important. Yesterday we learned how to take the operation of a limit on a function. Not as important as applications, but it's going to be really important for the two main things we do to functions for the rest of the year. And that is, I might as well say the words, we're going to take derivatives of functions and integrals of functions. So anyway, today, instead of talking about an operation of a function, we're going to talk about a property of a function. And this property is going to be really important for this third and fourth operation that we do. And that property is the property of continuity, whether a function is continuous or not. So, as with limits, I could give you a fairly simple definition that's very usable but not very mathematical or rigorous, or I can give you a more rigorous one. Well, I think both are important, but I'm going to start out with the fairly simple one. A function is continuous if you can draw the function completely without picking up your writing utensil, in my case, a crayon. So, with this simple definition, we can look at some functions that you're already quite familiar with, like the sine of x. Can you draw the sine of x without lifting up your crayon? You could start here, go down, up, down, up, down, up. It never has a place where you're breaking. So the sine of x, we would say, is continuous for all real numbers. Similarly, with the cosine of x. Cosine of x is very similar, it just starts at a different place. So the cosine of x is continuous for all real numbers. What's another function that we might know? The absolute value of x. F of x equals, sounds like a fairly complicated function, but we kind of know that it just makes a v. And I can draw that v without lifting up my crayon. So that is continuous for all real numbers. What's another really important type of function that we use all the time is polynomials. Whether it be a simple polynomial, horizontal line, straight line, a little more complicated, a first degree, a slanted straight line, or we go to a parabola of some sort, or even if we get to more complicated ones. They all can be drawn without lifting up your crayon. So all polynomials are continuous everywhere. This is good news because it's going to be really important that functions be continuous to do what we are going to do later in the course, these really valuable type things. So, let's try to develop a little more rigorous mathematical way, because this time we're really going to need to know this. First of all, let's just talk about a domain, all values of x between a and b inclusive. So on the closed interval, and let's just call C any interior point between A and B and find out whether a function is continuous there. Well, first of all, what are some necessary conditions? Does the function have to exist at C? Does f of c have to exist? I think it makes sense that if at a point C, you don't have a function value at all, there's nothing there, there's no way that you could draw the function through there. So certainly f of c must exist. Well, I wonder the limit as x approaches c has to exist. Well, think about this. For a limit to exist, the limit from the left as x approaches c has to equal the limit from the right. Well, if they don't come together at the same point, there's no way that you could draw that continuous line. So certainly, this is a necessary condition. But is it sufficient? Is it sufficient for just these two things to exist? Well, let's just come up with a counterexample if we can. Here's an example of a function where the function value exists, but the limit from the left does not equal the limit from the right. So the limit doesn't exist, the function value exists, so it's not enough just for the function to exist. Well, how about if both the function exists and the limit exists? Is that enough to call it continuous? Well, what about this example? What if this is c, and you had this? The limit from the left equals the limit from the right. Say that's 2. And now, I'm saying that f of c is equal to 3. So the function value exists, the limit exists, but would you call that continuous? No. If I'm following along here, I have to jump up to here and then come back down. I can't draw that without lifting up my crayon. So let's put those two things together. What if the limit exists and the function value exists, but the limit actually equals the function value? Not only does it come together at that point, but there's actually a point there. That should do it. So this is our rigorous definition. A function f of x is continuous at an interior point, x equals c, of the domain if and only if the limit as x approaches c of f of x, not only does it exist, but it equals the function value. So I'm even going to put a star there because that's going to be a really important definition if we have to prove that something's continuous mathematically. Okay, well, what's kind of an important theorem that we really can get from what we learned yesterday? This is a theorem. If f of x and g of x are both continuous functions at some interior point x equals c of the domain, then so are these other functions. F plus g of x, f minus g of x, f times g of x, f divided by g of x, a constant times f of x, and even the composite function f of g of x. Now, theorems have to be proven. I'm not going to go through all the proofs because if I do one of these, it's going to pretty much show you how you would do the rest of the proofs. So let's try to prove that if f of x and g of x are both continuous, that the function f g of x, which is really just a shortcut way for saying f of x times g of x. How do I show that that function is continuous? Well, what we might want to do is use this definition. Take the limit as x approaches c and see what you get. Well, yesterday we proved what I said, limits are our friends. In a more complicated way, we said the limit of f of x times g of x is the limit of f of x, and then you multiply it by the limit of g of x. That's just the way we would like it to be. So we know that this limit equals this first limit times this second limit. But since we know that these two functions are continuous, we know that this equals f of c and this equals g of c. So what have we proven? That the limit of this function, this product function, is equal to the f of c times g of c. We've just proven that it's continuous. So this, I've only proven one of them, but we have a good guideline for how you would prove the other ones, and this is a theorem that we can use. Why is that so important? What can I do? I can take a function like the sine of x and a function like a parabola, both of those that we know are continuous everywhere, and I can take a more complicated function like that, which we don't inherently just know what it looks like, and I can know that that's continuous everywhere because of that rule, that theorem right there. So, very important. Now, I've kind of skipped over endpoints. These are the interior points, and that's mostly what we're going to be concerned about. Just to let you know, if you were interested in finding out whether a function was continuous at the endpoint, like a, the only difference is you would take the limit as x approaches a, and the only way you can approach it is from the right. And that would have to equal f of a. And similarly for b, you would have to show that the limit as x approaches b from the left is the only way you could approach it. That would have to equal the function value. But I wouldn't be too concerned about endpoints. We're more going to be concerned about whether a function's continuous at some interior point, because that's what most of the points are. Okay, so let's just look at a couple examples here and see. Here's a rational function. A simple polynomial, a 0th degree polynomial divided by a 1st degree polynomial, a straight line. What do we know? We know that both of those by themselves are continuous everywhere. All real numbers. So we can say this is continuous for all real numbers. Ooh, with one thing that we have to add to this. What do we know? That you never can divide by 0. So g of x cannot equal 0. So right here, what's going to make this function equal to 0 is x equals -2. So we can't have that, so we would say except at -2. So anyway, here's a function that isn't so obvious what it looks like, and we were able to tell really quickly where it was continuous and where it wasn't. How about square roots? We can take the square root of any number as long as it's positive or 0. So all we have to do is guarantee that this function on here is greater than or equal to 0. So the way you do that is say this function is continuous for all real numbers, but x has to be greater than or equal to 3. Now here's a really complicated looking function. But what do we know? This is a composite function made up of the sine of x and this polynomial. Both functions we know are continuous everywhere. So by this part of the theorem, we know that this function is continuous for all real numbers. This is powerful right here. And let's go one more. What about the tangent of x? Well, you've learned that the tangent of x can be written the sine of x over the cosine of x. Both functions are continuous for all real numbers, but we know that the cosine of x is not continuous where x equals pi over 2, 3 pi over 2, negative pi over 2. So there's a lot of values where the tangent of x is not continuous, but most of the places aren't a problem. You kind of know that the tangent of x at pi over 2 has an asymptote. And at 3 pi over 2, it has an asymptote. So these would be places where you would have to pick up your writing utensil if you were to try to draw them. Okay, well that's pretty much all the ideas. Let's just look at 4 examples and then we'll be done. First of all, I'm taking a piecewise function made up of a straight line and a horizontal straight line. Well, what do we know? That both of these are continuous everywhere. So the only thing we have to really worry about is where the two functions come together. And they come together at 1. So I wonder if the limit, we know the function value exists at 1. We see right here, f of 1 is equal to 2, but we also said it's necessary that its limit exists. Well, what's the limit as x approaches 1 from the left? For values less than 1, then the function is x plus 2, so we put in 1 and we get 3. In other words, this function x plus 2 is a straight line until it gets to 1. It would look like that. And its limit equals 3. This function 2 is just straight across horizontally like that. And you can see pretty clearly that that's continuous everywhere except because the limit as x approaches 1 from the right is 2. Since the limit exists, we can say, since the limit doesn't exist, we can say that it's not continuous. So this function is going to be continuous for all real numbers except at 1. Okay, now we have a rational function, slightly different than this, not very much, it's got a 1 instead of a 3. But again, what do we know? For the same reason I said there, this function is continuous for all real numbers except at negative 2, because that's the only thing that makes the denominator 0. And both of these other functions are continuous everywhere. So that was pretty easy to see. Because what's happening here, the limit, well, first of all, the function value doesn't even exist, and we know it's a necessary condition, so we don't even really have to look at the limit. And we've got our answer. We have a function that really at negative 2, as x gets really close to negative 2, then we have a number divided by something that gets ridiculously small. So the whole thing is going to be going up to infinity. It's going to get really large. So we've got, I'm not going to try to get it perfect, but there's some kind of asymptote, either like this, or some combination. That we'll delve into that soon, as to which one they are. Okay, here, what do we know? A polynomial, a parabola, divided by a straight line. So it's continuous everywhere except where the denominator is equal to 0. Well, the only place that's true is at 1. So it's continuous for all real values except x equals 1. And if you wanted to see what's happening there, you could take the limit as x approaches 1 and look at it. You're going to get 0 over 0. They're not really 0, they're getting really close to 0 as x approaches 1. We call that an indeterminate form, not undefined but indeterminate. We're not sure what it is. It depends on how fast these things are approaching 0. So what we're going to do is do a little algebra. We're going to factor this into x minus 1 times x plus 1. And then when we divide by x minus 1, I can cancel out those factors and realize that this function is really just the straight line y equals x plus 1. So you've got a function that looks like that, except we know at x equals 1, there isn't a function value there. So it would look like that. But you can see it's continuous everywhere except at this point. Now, these actually have names. This particular type of discontinuity right here, where you go like this and then jump down to here, is not surprisingly called a jump discontinuity. This one, where the function goes off to infinity, is called just an asymptote. And this one, where the limit exists, but the function value doesn't equal the limit, so we don't even have a function value here, but the limit does exist, we call this a whole or a removable discontinuity. And the reason we call it removable is if I were to define h of 1 to equal 2, in other words, if this was the function at every place except for 2, but then I said let h of 1 equal 2, what could I do? I could just fill up that hole and it would be then continuous. We removed the discontinuity. Okay, last case, most difficult one. I doubt many of you know exactly what that looks like when you first look at it. It looks pretty complicated. But what do we know? Again, same thing. It's a rational function, polynomial divided by a polynomial. So the function is continuous for all real numbers except for x equals 1. Oh, I'm doing a very similar problem. I think I had one that was a little more difficult. I'm sorry. Let's go to x. I'm going to try a different one. Let's try k of x equals x plus 1 over x squared minus x minus 2. Okay, so we did that problem twice. So we hopefully got it right. This problem, again, is a rational function, and for the same reasons, it's continuous everywhere, except we have to find out, it's a little harder to see where the denominator is equal to 0. But if I were to factor the denominator into x minus 2 times x plus 1, then I can cancel, well, first of all, I can see that it's continuous for all real numbers except at 2 and negative 1. So we've solved the continuity problem. I'm just kind of curious what kind of discontinuity they are. Well, what can we do? We can take the limit as x approaches 2 of this function, and what do we get? Really, I can now cancel this factor with this factor, and the function really becomes 1 over x minus 2. That'll be, if we were going to take the limit, you'd want to do that algebra. So what do you get? You get something very similar to up here. As x gets close to 2, the numerator is 1, and the denominator gets ridiculously small, so that's where we have an asymptote. At x equals 2, we have an asymptote. But what's the limit as x approaches -1? Well, that one we can just plug -1 in there, and we get 1 over a -3. So that one really does have a limit. So at -1 and -1/3, right there we've got a hole, but the limit exists. So I'm not going to try to graph this perfectly, but we know somehow the function does this, has a jump discontinuity, and then has an asymptote. So we're, like I said, we're not sure exactly what this looks like, but it might look something like that. Anyway, that pretty much covers everything you would need to know about continuity this year. And this is the real big formula up here, and then knowing how to handle where a function is continuous by looking at limits and function values. So good. So thank you very much. Hope to see you the next time.